Hey, welcome. So today we're going to talk about something we all kind of get, steepness. We all know a steep ski slope from a flat sidewalk. But how do you turn that gut feeling into an actual solid number? Well, that's exactly what we're going to figure out.
I mean, really think about it. You see a line on a graph that's just shooting upwards, or maybe a road on a map. You know it's a climb. But is it a gentle stroll, or is it a major, leg-burning workout? That's the puzzle we're going to solve.
And this is where the magic of math comes in. We can take this vague idea of steepness and just nail it down to one single, really powerful number. And that number, as you might have guessed, is called the slope.
So the official term is slope, and you'll almost always see it written as the letter m. It's basically a fraction, a comparison really, that tells you how much a line is going up or down for every bit it goes across. It tells you exactly how fast that line is changing.
Now, slope breaks down into two super important parts. First, you've got the rise. That's your vertical change, how much you go up or down. That's going to be the top of our fraction, the numerator. Then you've got the run, which is the horizontal change, always to the right. That's the bottom of our fraction, the denominator.
And this all comes together in one beautifully simple formula. M equals rise divided by run. Seriously, that's it. This one little formula is all we're going to need to find the slope of any line on a graph.
Okay, enough with the theory, right? Let's actually see this thing in action. We'll kick things off with a classic positive slope. That's any line that goes uphill as you look at it from left to right. So we're going to find the slope between 2 points here, 0, 1, and 4, 3. The method is so straightforward. The most important rule? Don't guess, count. We'll start at the point on the left, and first we just count how many units we have to go up to get level with the second point. Then, from there we count how many units we go right to land exactly on it.
So what did we get? Let's look. Starting from that first point, we counted up 2 units. That's our rise, a positive 2. And from that spot, we had to move right 4 units to get to our destination. So that's our run, a positive 4.
Now for the easy part. We just build our fraction. Rise over run. That's 2 over 4. And of course, we always simplify our fractions. So our final slope is 1/2. What that really means is for every 1 unit this line goes up, it goes 2 units to the right. See? It's a precise recipe for steepness.
All right, let's switch gears and tackle a different kind of line. What happens when it's going downhill instead of up? Well, this is what we call a negative slope.
Our new challenge is to find the slope between the points 0, 2 and 2, -2. The process is exactly the same, but this time we have to pay really close attention to which direction we're counting.
Okay, so starting from our point on the left, we're not going up this time, are we? To get level with that second point, we have to go down 4 steps. And because we went down, our rise is a -4. What about the run? Well, we still count to the right, and that's 2 steps. So the run is a positive 2.
Time to build the fraction. Rise over run is -4 over 2. And if we simplify that, it becomes the whole number -2. That steepness is exactly -2. This tells us that for every 2 steps we go down, we move just 1 step to the right.
All right, you've totally got the basic method down. So now let's talk about a few common traps that people fall into. If you can sidestep these, you'll be finding slopes like a pro. First up, why do we keep it as a fraction? Why not just turn 2/3 into a decimal? Well, a slope's fraction is basically a set of instructions. 2 over 3 literally means go up 2, then go right 3. You can't count 0.666 spaces on a graph, right? Even when you get a whole number like 2, you should always think of it as a fraction, 2 over 1. Your instructions are up 2, right 1.
Now this is the #1 mistake, hands down. It's so easy to accidentally put the run on top, maybe because we're used to seeing x come before y. But trust me, m equals run over rise is always wrong. The correct way is always rise over run. The vertical change goes on top of the horizontal change. And here's a little trick to remember it forever. The y-axis is the one that goes high up and down, right? So just remember, y goes high. The change in y, the rise, always goes high up in the numerator.
And the second trap is just going on autopilot when you simplify a fraction. Look, in our first example, we had 2 over 4.
That correctly simplifies to 1/2. But in the second one, we had -4/2, which simplifies to -2. You can't just divide the bigger number by the smaller one. You absolutely have to respect which number is on top.
Okay, I get it. This is cool for a math class, but does this whole rise over run thing actually matter in the real world? Oh yeah, big time. And it shows up in places you probably see every single day.
Slope is literally built into the world all around us. Just think about walking up a flight of stairs. Your body develops this muscle memory for that exact steepness. And that's why building codes are so strict about it. If the slope isn't consistent, it's a safety hazard. So a standard staircase, it has a slope, a rise over run of 7 inches over 11 inches. If a builder messes that up, even on one step, that's the step everyone trips on. It's a perfect real-world example of why slope is so important.
And that's really the big takeaway here. You came in knowing what steep felt like, but now you actually have a precise mathematical tool to calculate the exact steepness of any straight line you see on a graph. Pretty cool, right?
So, you've totally mastered finding slope when you can see the graph. But what happens when there is no graph? What if I just give you 2 points, like 5, 10, and I don't know, 50, -80? How in the world would you find the slope then? Well, that's exactly where we're headed next.